Hi everyone, hope you're doing well and keeping safe. This is Ara from Team Hydrogen X. Our Capstone project is on solar fuels production unit. Our team members consists of myself, Mohammed Araf Haq, David Moines Flores, Thomas Licuris, and Matthew Tolentino. Our project plans to tackle the issue of global carbon emissions through the transportation industry. The objective of this project is to design and generate a feasibility report for a carbon-neutral hydrogen refueling station. In order to add realism to our loosely defined project, we started by choosing certain constraints. The design is to solely take input from solar while having the capability of drawing energy from the grid when necessary. We chose a particular location, Highway 5 sector in San Diego, with an area allocation of 3,000 meters squared. The goal was to be able to refuel at least 10 fuel cell vehicles per day. We mentioned our solar fuel of choice was hydrogen. Now, why did we pick hydrogen? Currently, we're seeing a large push towards battery storage for energy, whether it be for the grid or for use in electric vehicles. While this is fine for small and light applications, this technology does not scale well for storing energy for large grids and trucks due to energy density constraints. In recent years, there has been a slight inclination to introduce hydrogen-powered vehicles for their zero emissions and higher range. Additionally, hydrogen is a fuel that can be produced from completely renewable energy sources, which can phase out existing forms of non-renewables with modifications to fuel injection systems. By designing and simulating a solar-powered hydrogen production unit that is completely carbon neutral, we can analyze its feasibility in real-world applications to reduce emissions and pave the way for hydrogen infrastructure. And there are several distinct advantages that fuel cell vehicles have over their electric and normal counterparts. To begin with, hydrogen as an energy source is much denser than most forms of energy, coming at 120 megajoules per kilogram. That's 3 times more dense than gasoline. As such, fuel cell vehicles are generally more powerful and have longer ranges. This can be leveraged to more effectively power larger vehicles like trucks and buses. Furthermore, hydrogen storage is much cheaper compared to batteries, which can also undergo leakage in humid conditions. The most critical step of our design process was to choose our method of hydrogen production. We first turned to research papers to narrow down our selection on the basis of least carbon emission. Research conducted by Pandari and colleagues narrowed the selection down to 3 possible methods. The first option considered is steam methane reforming. In this process, natural gas is combined with water to form carbon monoxide and hydrogen. The carbon monoxide produced is then used again to react with water, producing more hydrogen, but also carbon dioxide. Although inexpensive as a means of hydrogen production, it would still be emitting about 25 kilograms of CO2 each time a fuel cell vehicle is refueled, which quite honestly is a deal breaker for us. The next means of production considered is biomass gasification. In this process, organic matter is reacted at high temperatures with controlled amounts of oxygen to form hydrogen and more carbon dioxide. This process of production is slightly cleaner than the previous as it emits only 20 kilograms of CO2 per fill-up. This is okay, but we can do better if our goal is to achieve as little emissions as possible. Well, this brings us to our method of choice: solar electrolysis. This method incorporates 2 things: solar panels, which harvest irradiant energy from the sun to produce electrical energy, and an alkaline electrolyzer, which will take the electrical energy and pure water to produce clean hydrogen and oxygen with no byproducts. Here, the only CO2 emitted is during the manufacturing of the components themselves, thus making it one of the cleanest methods of hydrogen production. After determining our method of hydrogen production, we had to go into further research for implementing our components surrounding solar electrolysis. Through careful time and consideration, we came up with our preliminary design model. The overall system is broken down into 4 main components: the power system, the hydrogen production system, the gas processing and storage system, and the control system. The green block surrounding the system encompasses everything that is within the scope of our project. However, certain things that are not included within the scope, like the compressor or the water pump, their energy is accounted for within the overall system to ensure realism. First up, we have the power system. The system is responsible for generating the electrical power needed to drive the overall system. It consists of a solar array and a grid-tied rectifier, with power electronics equipment for efficient AC to DC conversion. The solar array has 1120 solar panels to provide sufficient power for our refueling requirements. It serves as the main driving power for the overall system. It is directly coupled with the electrolyzer in our hydrogen production system to minimize power converter losses. The 3-phase rectifier within our power system can be used to convert AC power from nearby critical energy sources to DC for use in the electrolyzer during certain situations when additional power is required. This is put in place because the solar array is quite heavily dependent on the weather, and thus is unreliable at times. The hydrogen production system takes in inputs of pure water and DC power to electrolyze water to produce hydrogen. Our electrolyzer of choice is alkaline, and it is closely modeled to replicate commercial electrolyzers. This helps during the actual building phase of the design, since it can be easily replaced with vendor products. The gas processing and storage system consists of a storage tank in the form of a pressure vessel that temporarily stores the hydrogen produced from electrolysis. It is capable of storing about 200 kilograms of hydrogen at a time. The storage vessel accounts for the internal pressure and emits a signal to the control system when overfilled. Our Simulink model of the system also accounts for compressor energy loss, which is not within our overall scope of the system. Last but not least, we have the control system. This system monitors the other subsystems and ensures that the whole system operates correctly. It consists of a programmable logic counter that performs various functions, such as logging data, which consists of power, voltage, tank pressure, energy consumed, and many more. It also triggers key functions such as the pressure relief valve when our storage system is reaching full capacity, or commanding extracurrent energy from the grid from calculations gathered from previous days' weather data. Here we have the overall system realization in Simulink. Thomas will guide you through our tests and simulations from here on.
Hi all, my name's Thomas and I'll be taking you through our simulation and findings. For our simulation, we wanted to get an accurate depiction of the capabilities and running costs of our system to use as the basis for our feasibility report. To do so, the main driving force behind our simulation is data obtained from the National Solar Radiation Database, where our radiance and temperature data on a half-hourly basis are fed to our model inside of Simulink. The model is configured with 1120 400-watt panels and 280 electrolyzer cells with a cross-sectional area of 1 meter square in order to meet the site's refueling needs. To start, a year's worth of data was inputted from our location in San Diego to observe a wide range of operating scenarios. When run, our model keeps a running total of hydrogen produced, energy and water consumption of the electrolyzer, and power draw of the pumps and compressors needed for water intake and hydrogen compression. When the simulation is finished, these figures are output and ready to be analyzed for the feasibility of the system. In a year, our system generated a total of 22,200 kilograms of hydrogen, consumed 43,300 kilowatt hours of energy required for pumps and compressors, and consumed 198,000 liters of water. The overall buildup cost of the system can be estimated prior to conducting the simulation, but the simulation is necessary to determine the running cost and yield of it. Estimations show that the major components of the system cost about $1,800,000 to build, and the simulation shows us the overall running cost and hydrogen production. By using some cost constants for our location, we determined that the net revenue per year, neglecting the build costs, is about positive $183,000 per year. Unfortunately, over its 10-year expected lifespan, the future value of money invested at 10% per year is a more attractive option, as the build costs are too high for the system to break even by utilizing solar energy alone. Therefore, subsidies of about $450,000 are needed by the government in order to break even and make this a viable investment. As we just saw, our system has some weaknesses on the cost front, which is intrinsic of energy sources that are renewable, such as solar. Not only this, but a large area is required to implement this system, which may not be feasible for all use cases. Additionally, preventing the push towards hydrogen are companies which lobby against renewables, and the electrification of vehicles, which has amassed a larger market share in the transportation sector. Despite these drawbacks, this method of production utilizes a carbon-neutral process and has the advantage that it can utilize the existing electrical infrastructure to supplement solar input. This can even be a clean means of production if the grid is mostly renewables-based. Looking up for solar hydrogen, we have a global initiative to get to net zero carbon emissions by 2050. And additionally, with the increasing efficiency and lower costs with economies of scale, the cost per kilogram of hydrogen is starting to become more in line with other methods. Lastly, the key opportunity that hydrogen has going for it is its high energy density. Due to this, it can be utilized to fuel large transport trucks, an area where batteries will struggle due to their lower energy density and decreased hauling capacity. Although this project met all its technical user requirements, it is not financially feasible. It would require substantial amounts of government subsidy to break even. Either way, this gives us a comprehensive insight into current renewable energy infrastructure. As our modern society progresses towards higher energy demands for transportation, Hydrogen X will continue to develop more efficient methods of solar electrolysis models, resulting in a more practical framework. With potential improvements, this can help facilitate the hydrogen car inclination. As more car manufacturers adopt fuel cell vehicles into their lineups, there will be incentive to fund research and development into more feasible hydrogen production units to enrich the infrastructure. Let's drive towards a greener and more sustainable tomorrow.